Now let's talk about different ways we can get an electrostatic charge. The four ways we're going to discuss are friction, contact, induction, and polarization. Then we're going to go through each of these one at a time. Charging by friction is exactly that. It's when electrons are transferred by rubbing. Now remember, it's always the electrons that get transferred because the protons are bound in the nucleus. So when you brush your hair with this plastic comb, then the electrons go from your hair onto the comb, and you wind up with positive hair, and your comb becomes negative. When you rub cloth against, this looks like a rubber strip, you wind up transferring electrons. Now this is a very interesting apparatus where they were actually rubbing fur and collecting electrons. There are so many cool things you can do with by simply transferring charge by friction. So the first one is charge by friction. The second one is charge by contact, and this one is exactly what it sounds like. You are charging an object by touching it. So say I have a positively charged sphere and I'm going to touch this neutral metallic object, because in general you're going to touch, but it's usually going to be a conductor. It could be an insulator. If I were to touch this and it were a metal or a conductor, then some of the electrons would come from here and go and spread out nice and evenly all over my conductor here. Now, if this material was an insulator instead, I might have to touch it in several different places to get the charge even. Because remember, an insulator is not going to want to transfer charge easily, so it's not going to move. Now, the third way of transferring charge is transfer by induction. Now, induction is important because electrons move, charge is produced, but there is no contact. Conduction is always conductors. Induction is always done by conductors. Remember that. Induction has no contact, and it's always done with conductors. Let me show you an example. Suppose I have two spheres. This is just the classic one, folks. Now, suppose I have these two metal spheres and they are not charged. So that's very essential. These two right here have zero charge, zero net charge, or not charged. Now, suppose I were to bring, in this case, a negative sphere near them. Well, the negatives would push away the electrons because likes repel. And so this side would become positive and this side would become negative, but they're still touching, so the net charge is still the same. The net charge is still zero. Now suppose while I'm holding this close, I slide the second sphere away. Now, because it's touching here, the electrons can go, but as soon as I do this separation, the electrons are trapped on each sphere. So now this sphere has excess positive charges because it's pushed the negative charges to the sphere on the right. Now if I take the ball away, I now see that I have one negatively charged sphere and one positively charged sphere, and they will both have the same charge. Let's talk about grounding, because we're going to throw that term out there. Grounding just means that you've taken all of your extra charges and you put them somewhere like an infinite reservoir. Like the earth. Like you put them, into the ground. So the earth has a tremendous amount of positive and negative charges. If I were to dump 50 billion coulombs of charge in, it's really not going to affect the charge of the Earth at all. And so we talk about grounds a lot, and grounds are essential. So the Earth is our infinite reservoir here. Now we can do charging by grounding. Suppose I have a conductor, a wire here. This is some sort of conductor, and it's connected to the ground. By definition, it's going to be neutral. Now, suppose I bring a negative rod close. What's going to happen? Well, negative is going to push away all of the electrons. So the electrons, equal in magnitude to this charge right here, roughly, is going to be pushed into ground. And so this part of the wire actually becomes more positively charged. Now, if I were to separate it from ground, this is important. Once I separate it from ground, I can't spell, okay, it becomes isolated. There's nowhere for the charges to go to, and there no electrons can come back up from ground. So I separate it from ground and then remove my negatively charged wire. I now have a positively charged wire. And clearly, in order to get a negatively charged wire, I would simply bring in, of course, a positive wire. And when I do that, it will actually pull up negative charges from ground. And then you wind up with a negatively charged wire. Lightning is fascinating, and we always have an argument about whether does lightning go from the clouds to the ground or ground to the clouds, and the answer is yes. Remember, it is the electrons that travel. Electrons travel. So if the ground is very negative and the bottom of the cloud is very positive, then the electrons will flow up in lightning. While if the bottom of the cloud is negative and the bottom of the ground is positive, by another process we'll discuss in just a minute, then the negative electrons will go to the ground. We can have cloud-to-cloud strikes where the electrons go to the positive clouds, and you can have cloud-to-air strikes. So the answer for lightning is it can pretty much hit anything. And it can go from earth to cloud, cloud to earth, cloud to cloud, or cloud to the atmosphere. Lightning rods are excellent, and we're going to discuss why, when we do electric fields, you have this very sharp point, and they, of course, attract electricity. Because this becomes, let's say this is very negative. The electrons all run up here, and then discharge up into your clouds. Polarization is very similar to charging by inductions, but it's only in insulators. All right, charging by induction was with conductors. Charging with polarization is with insulators. Now, remember, an insulator, the electrons are not free to move. Because the electrons cannot move, they can't flow, but they can kind of scooch around a little bit. All right? Let's look at this Coke can. Oh, this is a conductor. All right. Let's not do this one. Well, this is an example of polarization. This is what happens near a wall. Say you have a neutral can. If you bring a negative charge close, it pushes the electrons away. And the positive charge, this side right here becomes positively charged. So the can itself is polarized. And polarized just means one side tends to be more positive, one side tends to be more negative. But the can itself is still neutral. The net charge is still 0. For example, if you were to polarize little strips of paper, and they could be collected by a comb. A water stream, and we'll do this in class, polarizes the water molecules. Water is a very polar molecule, and it wants to, which is one of the reasons it can conduct electricity so nicely. And we will actually bend a water stream with the Van de Graaff. Now suppose I have a balloon. Okay, we're going to pretend like this is a balloon right here. It says charged object, but it'll be a balloon. And say we have succeeded in charging this balloon positive. So we've been able to take away the electron, so our balloon is positive. When I bring it near a wall, which is neutral, all right, let's look at what happens. The positive charges attract the negative side of the molecules. So here we're talking about molecules. All right, and pushes away the positive side of the molecule. So this becomes an electrostatic charge. The balloon will actually hang on the wall, even though there is no charge transferred from the balloon to the wall. Physics in action, always cool.